Thank you. Yes, so I'm going to talk about this not so recent work about a measure of the city entropy from the perspective of an observer. Based on a 23 paper. Okay, maybe I ask you, since it's Blackboard talk, if I'm writing too small, please let me know. Also, if you have questions, I encourage you to ask in the middle, although it's not very common now. All right, so yeah, I'm going to talk about this subject, which is, I should also say that it's a very speculative computation or proposal, but at the same time, it's a combination of many ideas that have been floating around in the past 5-6 years. So almost all of the ingredients existed in one way or the other in the previous works. Okay, so the motivation is that basically we know that in the center, the space, we have a horizon. So if we consider an observer in the center, it has a horizon, and we can associate an entropy to this horizon, which is area over 4G. And we want to ask the usual question of whether we can give an interpretation of a Hilbert space to this entropy. Does this finite entropy mean having a finite number of degrees of freedom, a quantum mechanical degree of freedom that has a finite dimensional Hilbert space? Now, one of the consequences of having a finite dimensional Hilbert space is that at long times it leads to chaotic behavior. So one very simple example is that if I compute some correlation function, I can expand this in energy basis, where these Aij are some matrix elements, and e to the I delta Eij times t, where this sum over I and j goes over the energy eigenstates. If I have a finite dimensional Hilbert space, the sum is over a finite number of terms. So this correlation function might show smooth behavior. Let me call it G. This G of t, if I normalize it by its value at t equal to 0, might show smooth behavior at early times, but typically it decays, or maybe it oscillates, but its norm is decaying. But then at very late times, we expect that it should start doing some chaotic behavior. Now, for instance, interesting questions to ask is that what would be the average, long-time average of this G of t? Or what is the time at which the transition happens? We start seeing the chaotic behavior. Okay, so this is a consequence of having a finite number of terms in the sum. Now, if we have the state quantity interpretation of this entropy, we might expect that a similar situation is also true in the case of the Sitter correlation functions measured by an observer in the static patch of the Sitter. Now, if we go back to the computation of effective field theory, semi-classical gravity, the answer that we get for this correlation function, Gk of t, would be, let's say we are in this Sitter d plus 1. This Gk of t would go as e to the minus d t over 2 minus I mt. If I assume that this chi field that I'm considering is heavy compared to the expansion rate, which I set it to 1 in this talk. Okay, so as you see, as t goes to infinity, this goes to 0 smoothly. This is in contrast with the finiteness of entropy, and one can interpret this or think of it as a version of the information paradox. Which it seems like a contrast between unitarity or finite number of degrees of freedom and the effective field theory computation. This idea, this contrast was mentioned more than 20 years ago in the context of ADS black holes by Juan, and shortly after that by Susskind and collaborators in the context of the Sitter correlation function. All right, so now, of course, we don't expect from an effective field theory, from the gravitational computation, to predict this chaotic behavior for us. And recently we had lots of more experience about such situations that we know if perhaps if we formulate the question to gravitational path integral in a way that we are asking about coarse-grained quantities, we have a hope of getting answers that are consistent with unitarity, like computation of the entropy in the case of page curve. And however, we shouldn't expect from the EFT computation to give us these details. So in principle, we can hope that as in those other examples, we can hope that a semi-classical computation, or EFT, might give us the late time average of the square of the correlation function, or the transition time T star. Okay, so the goal of this talk or this paper was to present one toy computation that seems to suggest the existence of this transition and give us some time scale for this process. Okay, so toy. So this toy example is a 2D example using this famous JT gravity, the de Sitter version of JT gravity. Maybe I write some terms in the action, but not all of them. So it has been written in many talks. So there is a gravitational part of the action which has a topological term, a genus counting term, whose coefficient is a fixed number, which is going to, so this would be the analog of the Sitter entropy in higher dimensions. And then there will be a more dynamical term that contains a dilaton. There will be a boundary term that fixes the boundary value for the dilaton. Now, but in addition to this, of course, I want to compute a correlation function. And as a result, I have to add matter field. The matter field is just a free scalar field, so I wouldn't then write the action for that. Free massive field. And then, in addition, I'm also including a dynamical observer. It's very similar to what Jordan wrote in the previous talk. It's the dynamical observer with a dynamical clock on the worldline. And this is essential for being able to formulate the question I'm asking, because now here I'm asking about a bulk correlation function. And obviously, in a gravitational theory, I cannot define a bulk correlation function except in a relational way. So this observer is there to allow us to define this quantity in the gravitational path integral. In particular, it makes the time a dynamical variable that can be used. The time, one of the coordinates of this observer can be used as the argument of the field in the path integral. Okay, so in this model, for now we forget about matter and the observer, there are the Sitter solutions. And then if we put the observer and matter, we can get the results for this correlation function, which are in agreement with what we expect from the higher dimensions. We can also do it using more, of course, one can do it in a more traditional way, but one can also use the path integral and saddle point approximation to obtain it. Doing it that way is useful because then later on, I'm only going to look at the extra saddle. So I'm always doing just saddle point approximation. So therefore, it's nice to see how we get the original answer, this kind of behavior using complex saddles. This is a very standard computation. Again, I think it's been mentioned in other talks. So basically, this corresponds to computation of the correlation function in the Harte-Hawking state, which pictorially looks like this. So this would be our Harte-Hawking ket. But now we have a dynamical observer. So this would be a dynamical observer that lives in this geometry. And then we have the insertions of the operator along the worldline of observers. So let's say chi 0, chi t. And then there will be similarly the ket, the bra, along which the observer continues. And then this computation can be done at the level of the saddle point approximation, and one loop determinant gives us the expected result. So this computation gives us the g chi of t that goes as e to the minus t over 2 plus I mt. Let me just introduce some notation for drawings, so that because later I'm going to have more complicated drawings, so I don't want to draw this awkward whatever hyperbola. So instead of this, notice that this has the topology of a disk. So in the future, I'm going to draw this ket just as a disk with the observer worldline that goes in the middle, and then the insertions of the chi field would be like that. And then similarly, I have the bra. Oh, by the way, I should say that also for matter field, since it's a heavy field, I can use the semi-classical approximation, which means that also the matter fields can be treated as a worldline. Of course, this IMT just comes from its action, and then the decaying factor comes from the one loop determinant along this word line of the particle. All right. Oh, another thing to mention is that this phi b that I have here as a parameter in this action determines the boundary condition for the dilaton field here. So here phi is by B, and this final surface, I call it the reheating surface. And in these computations, the things that I'm fixing is the time separation between the insertions of this operator and the lengths of the reheating surface. And also the lengths, relative lengths of the two sides of the reheating surface, which in this case is a circle, with respect to our observer. Okay, so this is the computation for just g of t, which gives the standard answer. And then what we want to ask is that what happens if we compute this quantity, g chi of t squared, by using the gravitational path integral. And now, okay, then in principle, normally in if we computed it in a microscopic theory, it would just be the square of g chi of t. But again, recent experience tells us that in gravitational path integral, we can get the average answer of the microscopic theory by being a bit more or a bit unconventional in using path integral. And what we do is to apply the following principle that in computing this quantity using path integral, what I do is only fixing the boundary conditions, and I let the gravitational path integral to determine what is the bulk geometry. So in particular, when I try to compute this g chi of t squared, what is fixed is a bunch of boundary conditions which correspond to the fact that, for instance, I have, instead of 2 of these boundaries, I have 4 of these boundaries. I have the observers that go through and the time separation between the insertion. But I don't insist on the topology of the way these boundaries are connected to be a disk geometry. In principle, several boundaries can be connected to each other via a cylinder topology, which would be a wormhole. So what is fixed, therefore, in this computation would be so the reheating times, the number of observers, the time separation for the chi fields. Or in principle, one can also fix exactly the time of the insertions. And let's say the ratio of these two lengths on the reheating surface. So these are the fixed quantities, and then we look for a saddle with these fixed quantities. And now this turns out to get 2 contributions. One is just the square of the original one. And the other is something that looks like this. So there will be essentially one that contains a wormhole. Or maybe this is getting too small. This one. Okay, so there is, this is one geometry, which is the square of the original one. And there is another one which contains a wormhole. Okay, so let me just mention, make some comments. So these are the same as what we had before, just say the bra in the Hartree-Hawking wave function with an observer going through. Here is the ket. But now there is a geometry that connects the bra from one of those G's to the ket to the other. These are the reheating surfaces here. Why these two lines are identified. So this is not a boundary, but an identification. So here, therefore, the topology is a cylinder. And these are the insertions of the matter field. And what happens is that the matter fields are propagating through the wormholes. And the wormhole is destabilized because of the back reaction of the matter fields. Maybe I'll comment a bit more about this point in the future or in the next slide. But okay, so for now, if we accept this, that there are these contributions, now the first one obviously goes as e to the minus t is just the square of the previous answer. But this contribution will this contribution is, of course, suppressed by e to the minus SDS because it's a different topology. It's a higher genus topology. However, the time separation between these 2 points is no longer increasing as I increase t. So t is determining the time separation between these 2 insertions, while in this geometry, the time difference between these 2 insertion points remain finite. It approaches 2 pi. And therefore, this second contribution does not have that exponential suppression. As a result, the sum of the 2 eventually will be dominated by the last time, and there will be a time t star when the transition happens, which is of order of s this theta.
Not the log of this.
Why? Okay, how much time do I have? Okay, 10 minutes.
Should we worry that the probability that the blue observer disappears is bigger than e to the minus s theta? You remind us, say, the mass of the observer, the entropy of this observer.
I guess that was actually one of the comments I wanted to make. In principle, here the observer is taken as some rigid, eternal entity that exists. So I'm not including any probability for its emergence or disappearance. So yeah, in principle, you could ask this question, or maybe a related question is that if it makes sense to be able to measure a correlation function with precision of e to the exponentially small precision. Yes?
But didn't you also include the contribution where the observer goes through the wormhole?
Okay, that contribution has the problem that the length of the observer worldline remains finite. So if I think I can impose the condition that I want my observer to live long in a de Sitter phase. That's a meaningful extra condition to impose. Say again?
That does not conflict with the other boundary conditions?
So if I fix the length of the observer, this you can do. What it changes is actually one of the conditions that I did not write was to match the mass of the observer on the two sides. Let's say m ket equals m bra. since for this dynamical observer, if you remember the energy of the observer, by this mass I mean the total Hamiltonian, not just the bare mass in the Lagrange. Since the energy is conjugate to the time of the observer, then you cannot keep this condition. So then the mass would be different on the two sides, but the lengths can be made similar. However, okay, so if you keep this condition, so that the masses are different, the lengths would not be exactly the same, but they would be the same up to the very small corrections. The small meaning things that basically a constant, so it will be t plus some constant contribution.
Nature of this instrument? Just leave it as a time-like boundary with that, no? Would you get a similar answer? In that case, it would be eternal, it wouldn't disappear, so it wouldn't have to.
I'm not sure. It seems to be the case, but I don't exactly know what's the dynamic of time-like observers, so I don't know the answer. Like there should be something should specify the dynamics of this this time-like boundary, right, in this geometry. Uh-huh. But one might ask in some underlying description, perhaps also that is just a topology, right? There can be a fluctuation of that.
How about we save some more of this very good discussion to the discussion just because that thing is going to yell at us.
But yeah, I mean, I'm more or less done, but there is not much more to say. I have some more technical comments to make. Let me come here. But maybe these questions are actually more important than the technical comments. So one technical comment that I wanted to make is the importance of the observer. Here, the practical importance of the observer, as I mentioned, of course, it's there to make this computation well-defined to begin with in a gravitational theory, but maybe more practical at the level of the computation, it allows the energy momentum tensor to be conserved. So in particular, when I'm having these points at which I insert the operator, there is a change in the mass of the observer so that this vertex satisfies energy momentum conservation. So just to say that it was necessary to have this dynamical observer. A second technical comment is that this wormhole solution that I talked about, this solution without the back reaction of the matter field would not exist. So it relies on the back reaction of that matter field that I had there. Let me explain it a bit in more detail. So, and this also another technical comment related to my work, which is that many of the computation, many of the computation, in particular the wormhole computation, was done by starting from a Euclidean ADS solution and then analytically continuing to this theta. So it would be easier to show what is the construction of this wormhole in the Euclidean ADS case. which is very similar to a wormhole that was constructed in a paper of, I think, 21 or 20 by Douglas. Okay, so the idea is that in Euclidean ADS, so we have just a disk geometry. If I insert a matter field, it backreacts on this geometry of Euclidean ADS, ADS2, of course, which has a horizon. So after the backreaction, there will be two horizons. And then we can continue this construction by adding more matter fields. And the wormhole I'm talking about is basically obtained by cutting this solution, say here, and here, and then identifying these points. And then the fourth technical comment that I wanted to make is about the analytic continuation from Euclidean ADS to de Sitter. I'm using, so this here would be nice to think about a contour. So this is a kind of contour that people draw a lot when people discuss Hartree-Hawking wave function. So this is the complex T plane, this is the real T and imaginary T. The Hartree-Hawking wave function would be one that it starts from pi over 2 and then goes to large values of time. So this would be, say, T reheating. In this picture, if we think about, this geometry can be, the Euclidean ADS also can be drawn in this in complex T plane as being a contour that goes along I pi over 2. So this Euclidean wormhole that I'm constructing basically is obtained by analytic continuation of the ADS one to a contour that looks like this. So maybe to most of you, probably this doesn't make any sense or it's totally meaningless, but I'm sure to some of you has some meaning. So this is 2I pi. And then the insertions. So these are the two sides of the wormhole. As you see, they both have large real-time components. This T reheating is some very large real-time. And these are the insertion of the matter fields. And the contractions, normally it would be just between the matter fields inserted along ket or bra. So this is like one side, this is the other side, but now the contractions are happening here. So the reason why the lengths of that geodesics are not increasing with time is basically this. Or reason, one way of saying it is that these contractions are made in this direction. The distance between these 2 points is actually just 2I pi. Okay, so I should say this contour does not satisfy the Segal-Konsevic-Witten Konsevic-Segal-Witten condition on allowable metrics. Okay, maybe I just make two conceptual comments. How much time do I have? Oh, now it's gonna explode. But this is very short. So I wanted to. So this T star I said is order SDS. Notice that this is kind of obvious in a sense that since the leading answer is decaying exponentially obviously after this time scale, I get to exponentially small values. So if something doesn't change the exponential decay, there is one obviously get this as the time scale. Now, I should say that the fact that this is short is kind of reassuring, because if I have a microscopic theory of the Sitter universe, I don't expect it to work for exponentially long time scales, because one would perhaps expect that the Sitter universe is metastable, and after some exponentially long time scale, it decays. But this is a relatively short time scale, so we can have very reasonable scenarios of inflation which last 2 time scales of this order. However, this time scale was considered to be some analog of the page time, or argued to be an analog of a page time in a paper by Arkani, Hamed, Villadoro, Dubovsky, and Trincherini, I guess. And in particular, although these arguments are not very sharp, they show that there is a sharp transition to the slow roll eternal inflation at this time scale. So yes, if I have a slow roll inflation here, I didn't really consider slow roll, but if I have a slow roll inflation, this time scale has a meaning in that setup, meaning that I cannot have a non-eternal slow roll inflation for longer than that. Okay, so that's all I wanted to talk about. Thanks.
In your wormhole, there's a lot of time between the x's, right, along the blue curves.
There is a lot of time between these two, yes. A lot of Lorentzian time between these.
So if the blue curves, let's say they're close to each other at for the initial pair of x's.
These two blue curves?
Yeah. So
Uh-huh.
Isn't it kind of unlikely for them to remain close to each other at the later time also?
By closeness, you mean this distance being short?
Yeah.
Well, this in a sense, what happens is that this distance, well, this is a complex geometry. What happens is that actually there is a long Lorentzian distance which is positive, then some amount of Euclidean distance, and then another long Lorentzian distance which is negative, so they cancel.
Those Lorentzian distances are not for like aligned generators, then the distance could end up being large still. Like if the blue curves are not exactly parallel, then the distances could be large.
Yeah, I'm not sure. Yeah, maybe I don't understand.
Would the same question arise for the ADS version?
No, in that case, they have to be aligned in order for the SL2 charge to be 0.
But by aligned, you mean a relative shift between this and that? So you are thinking about just shifting it on this side?
I don't mean a time translation. I mean like
it's not a time, but it's a space. Like, are you thinking of rotating these insertion points on one side with respect to the other?
Well, yeah, some rotation. I don't want to commit to exactly what.
But I just don't understand what you mean by aligned.
Well, you have a sphere. The topology of a sphere, and you have two circular trajectories that are.
But maybe you want to explain it here. No, isn't it easier here? By a line, you mean that this length is on one side might be different from the other? Is that your notion of being aligned and not aligned?
No, I'm not talking about the particle trajectories, but the observer trajectories.
The observers basically are determining the points at which the particle is being emitted. Right, because the particle is attached to the... So I just don't understand what you mean by a line. Does it mean that the points at which the particles are attached is going to have this diagram is going to be asymmetric? Like here there will be larger separation.
You have some sphere with two circular trajectories on it. And maybe the circular trajectories are not exactly parallel, so that if they're close to each other at t equals 0, as measured by their respective clocks, they're not close to each other at time t. I don't know anything that, well.
Yeah, I'm not thinking of it as two lines on a sphere. At least I couldn't bring everything on a sphere. If you want to embed it inside this Sitter geometry, it is, okay, it has some portion of the global de Sitter, but it has portions which are Euclidean and Lorentzian. So I cannot embed the whole thing in a sphere, but perhaps there is a way to do.
I think the question is, did you calculate the one loop determinant of this quantity?
Well, no, I didn't do the one loop determinant computation. But you are worried about having some negative modes, instability.
Determinant, because to make the trajectories close to parallel would require some each of the minus t tuning.
No, yeah, I don't know. I haven't. I just computed the lengths of these trajectories, and the lengths are what I'm reporting here.
One more question. In the Euclidean black hole, there's an interesting phenomenon that the average of G, has a ramp and a plateau itself, and that's produced by a genus-1 correction, paper by Phil Saad. Do you have a similar effect here? Or do you expect a similar effect?
To have a ramp?
And the plateau, yeah. You're consistent with that?
Well, this, I don't know. I don't have any expectation. Is the one? I think one comment that I can make is that in the black hole examples, the ramp is coming from geometries, is double cone geometries that exist even without the back reaction of the matter field. Like the same geometries that give you the ramp in the spectral form factor would give the ramp in the correlation function. And that therefore it doesn't require the back reaction from matter fields. Here, you can look for such geometries, but those geometries might exist. I'm not sure. I'm not sure in this Sitter whether they exist or they can match with the boundary conditions that I'm imposing here.
All right, let's take Mehrdad again.